Okay, so now that we have risk-neutral probabilities of default, we can move to pricing the bond, okay? But just before doing that, we do one more intermediate step, which is to convert the probabilities of default that we have to these default intensities. So this is typically done in these credit risk models. You can think of this as converting, when you take an interest rate and convert the annual interest rate to a continuously compounded rate. So it has the same type of flavor. So you have a probability of default, and instead of using the probabilities we've been doing so far, you convert it to this lambda here, which is a default intensity. And the nice thing about this is that you can have the default intensity varying through time as you want, okay? So this example here shows you how to work with this default intensity, and then we'll work with this a little bit more in the following chapter. So for now, let's just say that I have a default intensity of 5% per year, so a lambda in this expression here. Let's see how that can be, how this lambda can be converted to the usual probabilities we have been working with so far. So we have here some examples. The probability of survival for 1 year comes directly from this formula here, when you replace the lambda by 0.05, and the limits of integration are between 0, the starting point, and 1, the final point. Okay, so let me show you the detailed calculations here. So again, we're assuming for now that the default intensity is constant, 5% for all periods. In general, this can vary with time. That's the nice thing about this feature here, but to make this simple now, it's constant. So again, the probability of surviving for 1 year is the exponential of minus the integral from 0 to 1, 0 to 1, of the lambda 0.05, and that's it, right? So evaluating the integral, it becomes this expression here, and the number turns out to be this one here. So once you have the probability of surviving from 0 to 1, we already know that the probability of defaulting is what is left. So it's 1 minus that probability of survival. So the probability of default for 1 year, it's 488%. So notice that it is close to the 5% we started with, but not exactly 5%. And again, intuitively, it's the difference between, for interest rates, what would be an annual rate with annual compounding and a continuously compounded rate. So it's not exactly that, but it's this type of idea. We're just taking the same underlying probability of default and either expressing it in one basis or in a different basis. Okay. What is nice here also is that you can, once you have the lambdas, you can very easily get probabilities for whatever horizons you want. So the probability of surviving between 0 and 2 years from now comes directly from the equation. So it's just the exponential of minus lambda times the distance between 0 and 2, which is 2. That would be 90%. If you want the probability of default over a very short period, say 1 month, you just take 1 minus the probability of surviving 1 over 1 month. The probability of surviving over 1 month, it's the usual exponential of minus the integral from 0 to 1 over 12 and so on. Since the lambda is constant, it becomes this very simple expression, 0.42%. Okay. So going back to the handouts, let's now do the risk-neutral pricing. Okay, so we're going to use exactly the same setup as before. We think of the bond evolving like a tree. We are alive now, then 1 year from now we're either alive or in default, and then we branch for 1 more year and keep doing like that. So it's exactly the same tree as we had before, exactly the same pricing equation as we had before, now adjusting for these new probabilities. So where before we had here objective physical probabilities and we concluded that that would not really work, now we have replaced them by these risk-neutral adjusted probabilities, as you see here. Okay, and accordingly, we are now discounting at the risk-free rate. So these z's that you see here are the discount factors that come from the risk-free interest rates, right? So now everything is consistent. I know how to get risk-free rates. I know how to get risk-neutral probabilities of default, and there is no longer that problem we had seen before of double counting the default risk. Now everything is consistent, and I can get the true price of the bond. Okay. Some notes here. Please read through this. This explains how some of these probabilities are computed. So, for example, the probability of surviving between 0 and a very long distance can be broken in these two intermediate steps. Okay, and then the probability. So this part here is the probability of surviving up to the beginning of one period and then defaulting over that year. Okay, and that, so if you think of a tree like you had here before, like here. So for example, what we're saying in that formula there is that the probability of going from here to here to here and then defaulting here, so the probability of this branch can be computed just using probabilities of surviving. So it's going to be the probability of surviving up to here, the beginning of the period, minus the probability of surviving up to the end of that period. Okay, so going back to the equation here, I was just describing this step here. The proof is down here in the footnotes. You can look at this later on. Okay, so let's look at this example where we want to find the price of a 2-year bond paying 7% coupons with the following assumptions. Now, the default rate varies through time. That's the nice thing here. I can make this lambda vary through time as I want. So it's 1% for the first year, 2% for the second year. The recovery rate is 40%, and the risk-free rate is flat at 3%. Okay, let's see how we compute this. So you have all the details here, but let me open the picture with another explanation more in detail. Not this one, this one. Okay, so this is the bond. We are at time 0. We want to find the price. 1 year from now, it can either be in survival or in default. If it is in survival, we get the coupon, 7%. If it is in default, we get the recovery rate of coupon plus principal. If it is in survival at the end of the first year, 1 year from now, again we branch to either survival or default, and these are the cash flows, right? So to price, I need to have all the probabilities of all these branches to then apply the formula, right? So the first one, the probability of getting to state S1 is the probability of surviving between 0 and 1, which is again the exponential of minus the integral of lambda over between 0 and 1, right? So lambda is constant over the first year. So in that case, it's just a simple expression like you see here, which gives me a probability of survival of 0.99. So that's the probability of going from here to here. Now, second step, the probability of surviving up to time 2. So, which is this b here, the probability of surviving from 0 to 2. So, according to the definition, it's the exponential of minus the integral from today until the end, till 2, of lambda. But now I have to be careful that lambda changes, right? It was 1 in the first year, but now it's 2% in the second year. Or if you plot lambda through time, it looks like this. It's flat at 1 for the first year, and then 2% for the second year. Okay, so now this integral breaks down in these two different areas. The first part is the integral of this initial rectangle, so it's the integral is the area of this small rectangle. So the value of 0.01 times the distance, which is 1 minus 0. And then the second part, it's the area of the second rectangle here. The lambda is 0.02, and the length of the rectangle is 2 minus 1. Okay, and that gives us the probability of surviving from 0 to 2. Now, next, the probability of defaulting in the first year. Okay, the probability of defaulting in the first year is just, as we know, it would be just 1 minus the probability of surviving. But if you look at the formula that you see in the notes, this is the full formula. So it's the probability of surviving up to the beginning of the period, which in this case is the probability of surviving up to now, given that I am alive right now, and that probability is 1, times the probability of defaulting over the next year, so from 0 to 1 in this case. So 1 minus this probability we had here, 0.01. Last, D is the probability of getting to D2, which is the probability of surviving the first year and then defaulting over the second year. Okay, so again, if you look at the formula, what you see there is that this probability, surviving the first year, defaulting in the second year, can also be computed as the probability of surviving up to the beginning of the period, so until here, minus the probability of surviving up to the end, to the end of the period. until from 0 to 0.2, which is this expression you see here. So 0.99 is the probability of surviving for the first year. 0.97 is the probability of surviving from 0 to 2 that you see here. And that gives you the probability of this branch going from here to here, and then from here to here, 0.0196. Okay, so now the value of the bond is just the sum of all these cash flows discounted back to today at the risk-free rate, multiplied by the corresponding probabilities. So the first cash flow here from A is 0.7%, discounted at the risk-free rate, times the probability of that case, plus the second cash flow, B, this one here, which would be face value plus coupon, discounted back to today at 3%, times the probability of getting there, which we have already computed, 97. And so on for the case C and for case D that you see here, right? And then the sum of these four values gives you the value of the bond today. Okay? All right. This part here is a general formula that we are not going to cover in this class, so you may ignore this general pricing formula. All right, thanks.